In any calculation, we often deal with various quantities with different dimensions. Let's see what can be done with dimensional quantities. We can have any power function of a dimensional quantity, such as f of x is equal to x to the power k. If the dimension of x, which is denoted by bracket of x, is capital AX, then the dimension of f of x is capital X to the power k. Any polynomial function is meaningful if all of its terms have the same dimension. For example, these two terms should have the same dimension. Here, a and x and b may have dimension, but a times x to the power 2 should have the same dimension as b times x to the power 3. In fact, if their dimensions are not similar, we cannot add them together. Let's consider the sine function. The argument of a sine function is in radian. That is defined as the ratio of two lengths, the arc length and the radius of a circle. So it's dimensionless. Let's consider sine of AX. Then AX should be dimensionless. Moreover, we can have a Taylor series expansion for sine of x. It is the addition of different powers of AX. If the dimension of AX, for example, is length, then in the above Taylor series expansion, the first term is length, the second term is volume. It's meaningless to add length to volume. So AX should be dimensionless. And this is not correct. The arguments of functions like sine, cosine, exponential, hyperbolic tangent, and so on and so forth are also dimensionless. The analytic functions have Taylor series expansion, so the arguments of any of these functions is dimensionless. If we investigate the dimension of the physical quantities we are familiar with, we may probably see that they are in the form of power law. Let's consider length. Its dimension is L. The dimension of area is L squared, and the dimension of volume is L to the power 3. Dimension of acceleration is Lt to the power minus 2, and the dimension of energy is ml to the power 2t to the power minus 2. All of these are in the form of a power law. Does there exist any other function? Let's consider the quantity q, whose dimensions are d1, d2, and etc. Then, is there any general theorem on the dependence of the function f on its arguments? Let's consider, for simplicity, q only depends on one dimension, the dimension of q. For example, its dimension depends on one dimension, for example, length L. We want to know the functional form of f on L. Take a system of units in which the numerical value of q is 1. Then q is a quantity whose numerical value is 1 and whose dimension is a function, an unknown function of L. If we choose another system of units, its numerical value will change. For example, suppose in the original one, the length is 1 meter, and there are two other system of units, A and B, where the unit of length are 1 centimeter and 1 millimeter respectively. So we consider three system of units. In one of them, the unit length is meter. In the other one, 1 centimeter and 1 millimeter. As it is seen here, the unit length in the system of units A is 100 times smaller than 1 meter, and in the system of units B, it's 1 over 1000 with respect to the original system. Then the numerical value of Q in systems of A and B are as following. In the original system, its value is 1. In the system A, it's 1 times f of, in this case, it's 100, but in the general case, we assume it's alpha. I mean, in the original system, it's alpha times larger than A. The system A unit length is beta times the system B. Then QA is f of alpha and alpha beta, because the unit length in the original system is alpha beta times unit length in the system B. Q in the system B is also can be written as Q alpha F beta, because the unit system is in the system of A is beta times the unit system units length in the system B. From these we can obtain F alpha beta is equal to, we should solve this equation to obtain the functional dependence of f on its argument. If we assume the function f is continuous, we can prove that it should be a power law function of its variable. Means f alpha is alpha to power something. For example, yeah.